Hello everyone, my name is Kalptaru Agarwal and I am going to give a presentation on application of Fourier series. So let's begin with the introduction of Fourier series. The Fourier series is an expansion of a function in terms of sines and cosines or imaginary exponentials. It is basically the summation of sine functions with different frequency and amplitude. The series is defined in its imaginary exponential form as a function ft that is equal to summation an e to the power iota nx, where n goes from minus infinity to infinity. In this equation, an stands for 1 by 2 pi times integral of f of x e to the power minus iota nx dx, where integral goes from minus pi to pi. These are some examples of Fourier series for some simple waveforms. You can see that all these waveforms are represented in form of summation of sines. Okay. Now we will start with the application of Fourier series. The Fourier series is only capable of analyzing frequency components of certain discrete frequencies for a given function. But function with continuous frequency components can also be analyzed using the concept of Fourier transform. The imaginary exponential form of Fourier transform is defined as h omega, that is equal to integral h of t e to the power I omega t dt, where integral goes from minus infinity to infinity. Now we can take n equidistant discrete frequencies in range minus omega c to omega c. Such approximation to Fourier transform is given as h omega, that is equivalent to delta. Delta is difference between two uh, uh, consecutive frequencies that we are considering. So h omega equivalent to delta times summation of hk e to the power iota k 2 pi n by n, where k goes from 0 to n minus 1. This equation is called discrete Fourier transform of function ht. Currently, the most common and efficient method of numerically calculating the DFT is by using a class of algorithm called fast Fourier transform, or FFTs. It can be shown that one may divide any DFT into a sum of two DFTs which each correspond to n by 2 minus 1 points in same frequency range. The most useful part of this formula is that it can be used recursively, since each of these terms may independently expanded using the same algorithm, each time reducing the number of calculation by factor of 2. This FFT algorithm, the Cooley-Tukey FFT algorithm, shrinks the computation time from order of n square operations to much more manageable order of n log n operations. This algorithm is so fast that it is used in modern digital oscilloscopes and many electronic equipments. FFT is also used for numerical computation, arbitrary size multiplication operations. Another important application of Fourier series is spectrum analyzer. This instrument is broadly used by experimentalists. This instrument reads a signal and provides the operator with the Fourier coefficients which correspond to each of the sine and cosine terms of the Fourier expansion of the signal. It is so widely used that now comes built in. It now comes built into oscilloscopes. Spectrum analyzer is most commonly used for noise signal studies, as FFT of the signal gives the amplitude of various oscillatory components of input, using which experimentalists can determine that which frequencies dominate their signal. For example, if we have a DC signal, you would expect that FFT to show only very low frequency oscillations. That is, the largest amplitude should consider to correspond to frequency that is equivalent to zero or almost zero. However, if we see a sharp peak of amplitude around 60 hertz or any frequency, you would know that something is feeding noise into your signal with a frequency of 60 hertz. For example, an AC leak from power source. So this is a very useful application of spectrum analyzer that we can. Digital signal processing. It is also done using a form of Fourier series. We have already seen how Fourier series allows experimentalists to identify the source of noise. It may also used to eliminate source of noise by introducing the idea of inverse fast Fourier transform, or we can say IFFT. In general, the goal of IFFT is to take the AN and use them to reconstruct the original function FT. Analytically, this is done by multiplying each an by its prefix, that is e to the power 2 pi iota k n upon n, then taking the sum over all n. However, this is an insufficient algorithm to use when the calculation must be done numerically. You can calculate the IFFT directly from FFT. To do that, you need to simply flip the real and imaginary parts of coefficients calculated by the original FFT. There are many advantages of doing DSP, digital signal processing, as opposed to doing analog signal processing. To begin with, practically speaking, you can have a much more complicated filtering function in digital signal processing than in analog signal processing. Furthermore, even if a more complicated filter was implemented with analog electronics, it is difficult to make even small modifications to filter. While digital signal processing is not limited by either of these effects, since the processing is done in software, which can be programmed to do whatever the user desires. Probably the most important advantage that DSP has over analog signal processing is the fact that the processing may be done after the signal has been taken. In modern day experiments, raw data is often recorded during the experiment and corrected for noise in software during the analysis step. Suppose if one filters the signal beforehanded with the analog signal processing, it is impossible that that in later experiment the experimenter could find that they filtered out good signal. The only option in this case is for the experimentalist to rerun the experiment. On the other hand, if signal processing was done digitally, all the experimenter all that the experimenter has to do is edit their analysis code and rerun the analysis. This could save both time and money. Analytical applications. The Fourier series also has many applications in mathematical analysis. Since it is a sum of multiple sines and cosines, it is easily differentiated and integrated, which often simplifies analysis of functions, such as saw waves, which are very common in signals in experimentations. Some analytical functions we use are discontinuous functions and convolution. The Fourier series, so now we are going to talk about discontinuous functions. The Fourier series also offers a simplified analytical approach to dealing with discontinuous functions. Nearly every function encountered in physics, both continuous and discontinuous, may be represented in terms of Fourier series. This gives Fourier series a distinct advantage over Taylor series expansion of a function, since the Taylor series places much more stringent limits on convergence that the Fourier series don't. For example, you can take that Taylor's series require a function to be continuous to be valid. Convolutions. The convolution theorem states that Fourier transform inverse Fourier transform of f and Fourier transform of g is equals to f into g, where f denotes the since the Fourier transform may be approximated by a Fourier series, FFT algorithm may be applied for numerical calculations of the convolution. In fact, the FFT method is preferred method of calculating convolutions, which prevent the need of direct integration. Okay, so to conclude my presentation, I would like to just say that the Fourier series is useful in many applications, ranging from experimental instruments to rigorous mathematical analysis techniques. Thanks to modern developments in digital electronics coupled with numerical algorithms such as FFT, The Fourier series has become one of the most widely used and useful mathematical tool available to any scientist. Moreover, I want to say that these were the some applications that we have already discovered. But I think that there are far more possibilities there to be which can be solved using Fourier series. Okay, thank you.